All right, so yesterday we were looking at kind of the conceptual understanding that we need for an angled launch problem. And typically you will be given the speed and the angle of launch. And that was kind of represented here. So 58-degree launch would be, 45 would be right down the middle. 58 is going to be higher than that. And what we knew coming in is kind of this angled vector here, 4.7 meters per second, is what we would call the launch speed. What we need to know about once it becomes a projectile is that the acceleration is only downward, right? Gravity is going to pull this thing down as it moves. There's no left or right force that's going to change the velocity. So if you look at kind of the diagram here, the x component to velocity is constant. And I could have even put a little hash mark on it if I wanted to. And that's the same as what we looked at with horizontal launches, right? Because the acceleration is downward, the starting velocity that's upward gets less and less. At its peak, Vy, so the up-down velocity is 0. That's a fact that we want to remember. It's going to help in problem solving. And then just like something thrown straight up, it's going to start to speed up in the downward direction. The only difference here is that it also has some rightward motion at the same time. Okay. So we did free fall problems way back in first quarter, I think. We're going to use some of that same thinking to think about what happens in the y direction. Right? So usually the next step is to do some trigonometry and figure out if this is my launch speed and this is my launch angle. Well, how much of that is in the x direction and how much is in the y direction? So I used cosine of 58 to solve for the x component, the starting x component of the velocity. And it comes out to be 2.5 meters per second. So that was just the full 4.7 meters per second times cosine of 58. And in a similar way, the starting y velocity is going to be the full 4.7 meters per second times sine of 58. And we can see, as expected, the upward velocity is bigger than the sideways velocity to start because of the 58-degree angle. Right. So any questions up to that point? All right, and you wouldn't necessarily have to do it, but we went ahead and wrote some general equations for the x direction motion and the y direction motion. Our general position equation that we've been using, again, since probably first quarter. The first term would be half the acceleration times t squared. In the x direction, there is no acceleration, so that term is 0. We go to the next term. It's the initial velocity times time. The initial velocity in the x direction is 2.5. That's a place where students get tripped up. They see V0 and they think, oh, it's 4.7. That's the angled velocity. We're dealing with just the x direction as its own kind of problem set and the y direction as a completely different problem set because we have acceleration in one and no acceleration in the other. And then it's easiest to just say that this launch point is horizontal position 0. So that last term, the initial position term, gets dropped as well. If I wanted to write the velocity equation, which I did over here, velocity, the general equation, is acceleration times time plus your starting velocity. Well, again, in the x direction, the acceleration is 0. So it's really just making a statement that Vx is always 2.5 meters per second. It's not going to change in the x direction. All right, questions in the x direction? All right, y direction. We go back to our general equation. Now we do have an acceleration. The acceleration is caused by gravity, and we're going to use negative 9.8 meters per second squared as the acceleration due to gravity. In the general equation, the t squared coefficient is half of the acceleration, and that's why I'm plugging in negative 4.9 here. It's important that it's negative because it's a downward acceleration. The middle term, v0t, that's the starting velocity times time. Again, I don't want to use 4.7. I want to use the starting y velocity, 4.0 times time. The x0 term here would be y0, the up-down initial position. And for an object that is launched and caught at the same height, or launched and lands at the same height, it's easiest to just say that that initial position is 0. Okay, so that term drops out of the equation. Now the velocity equation, again, it's the acceleration, not half, but the full acceleration, negative 9.8 meters per second squared times time, plus the starting velocity, which was, again, the velocity in the y direction, the 4 meters per second. Okay, so this equation would tell me the velocity at any time. Okay, those of you who know some calculus, the derivative of this equation is the velocity equation, right? That's how those two fit together if you know some calculus. Right? All right, so that gives us a good setup for solving our problems. So I think we quickly drew the graphs yesterday. Let's think about those again. I lost them somewhere along the way. So the horizontal, so my x direction versus my y direction. In the horizontal, I start at position 0, and I have a steady increase in position, a slope of 2.5 meters per second, going to be linear. The velocity graph is just steady, right? And I even know so much that it's going to be at 2.5 meters per second. And in the x direction, the acceleration graph is just 0. When you're accelerating, sometimes I think it's easier to look at the velocity graph first. So it started with an upward velocity of 4 meters per second. I'm going to start somewhere up here. And because acceleration is downward and slowing it down, it's going to slow down to 0 at its peak and then continue. Should be a straight line. Something like that. So it slows down to rest. It begins to fall and get a more and more negative velocity because of that acceleration. The acceleration here is a steady negative 9.8 meters per second per second. And the position graph, which I think is often the most difficult, it starts at height 0. It starts with an upward velocity, so it's going to start with a positive slope. It's going to gain y position, and as it gains, it's slowing down. So the steepness of the line needs to round out and be parabolic, and then it's going to fall as well. So that 0 time would be here. That's kind of messy, but hopefully you can get the gist. All right, so we want to know how long the ball is in the air and how long it takes to reach its peak. There are a couple of ways to go with that. Let's do time to peak first. So I want to know time to peak would be whatever this time is. I put 0, but that's when velocity is 0. I want to know how much time it takes to get to that peak point, or how long it takes to go from 4 meters per second to 0. So for peak time, I like to actually use the velocity equation. how long it's in the air is completely dependent on the y direction, right? Going up, coming down, okay? So if I go to my velocity equation for the y direction and I set it equal to 0, that's going to be the time it takes to get to y velocity 0. It gets to y velocity 0 at the peak time. Maybe I should just call it t. Okay. So if I take my y direction velocity equation, and I'm going to leave off units, although they do work out if you follow it through. If I solve for t, that will be time to peak. So my algebra would be to subtract 4.0, divide by negative 9.8, and that should equal t. Let me grab my notes. All right, so 4.0, I can make it negative if I want, divided by 9.8, which is also negative. And I get a decimal value less than 1 second. I'm going to keep 2 significant digits, so I'm going to call it 0.41 seconds. And again, that is time to peak. Plug my tablet in here. It'll be a little bit better. All right. Now, if you had to guess, total flight time, there's some symmetry here. You might think, and you're correct, that if you just doubled the peak time, you would have the total flight time. That will be true when you launch and land at the same height. So it is okay to make the assumption that the total flight time would be 0.82 seconds, just doubling it. I could do this another way. If I go to the y position equation, what I'm interested in is the time it takes to get to position 0, right? Launch and land at 0. So I could, I think I'm going to zoom a little bit. If I can. Give myself a little bit more room to work. If I go to the position equation and set it equal to 0, that's going to be the time it takes to get back to y position 0. So that's going to look like 0 equals negative 4.9 t squared plus 4.0 times t. So the way I like to solve this one is actually to factor out a t from both terms here. So if I factor out t, I've got negative 4.9 t. That's just factoring a t out here. If I factor a t out of 4.0 t, it's just 4.0. And then to solve for that, I know either this t equals 0, so that's one solution to the equation, or the quantity here equals 0. Okay, that's a 0. So my algebra here is going to be to subtract 4.0, divide through by negative 4.9. And that will equal t. Now this t would be how long it takes to get to position 0. And just checking it on the calculator. We know what it should be, and we get confirmation that it's 0.82. All right, so we predicted it would be that. Notice we did have two solutions here. T0 is also at position 0 because it's at its start height at time 0. And then when 0.82 seconds pass, it's back at position 0. So that would be, 4.1 seconds to get here, 0.82 seconds to get here. All right. Okay, now how far does it go? We want to know how far does it move horizontally in the full flight time, in 0.82 seconds. Right, where are we? In the x direction. Well, the x direction equation was just the speed, the x speed, or x velocity that doesn't change, times time. And I want to take the full time, and I will put in the units here just to show that it works. The t that I want to use is the full 0.82 seconds. Got a little delay on my pad here. Okay. So that's going to be how far does it go in the x direction. So a little over 2 meters. We'll call it 2.1. Oops. And that would represent, going back to our first diagram, this distance, 2.1 meters. Okay. And then we have, what is the maximum height above launch position? Height is referring to the y direction. So I go back to my y equation. Now I want to plug in not the full 0.82 seconds. I want to plug in the peak time, half of the flight time, to determine peak height. So I'm going to go back to my y equation, negative 4.9. That's meters per second squared. I'm taking the half flight time, squaring it. So meters per second squared times seconds squared would go to meters. And then again, I want to not put in the full velocity. I want to put in the starting y velocity, the 4.0 number. That's meters per second times time. Again, it's the peak time, 0.41. It is important that this term is negative and this one is positive. So let me take 4.9 negative times 0.41 squared equals so this comes out to be negative 0.82, that would be meters. This term is going to be positive. So 4.0, which is 4 times 0.41 equals 1.64 meters. And if I add them up, it should be positive 8.2 meters. So not quite a meter of height gained at its peak. Okay, so that would be this height. .82 meters. Okay. Now you might wonder, it was half, right? The two terms were, this is, half of 0.164. If you go back to another way that we found displacements or changes in positions, the area under a velocity plot is another way to find position change, right? Displacement. So if I were to find the area of that triangle, it would be 1/2 times the base. The base of the triangle to get to 0 velocity, that was the 0.41 seconds, right? The half flight time. Base times height, it's a triangle. The height of the triangle is the starting speed in meters per second. So if we take 1/2 of 4, I'll make my math easy. 1/2 of 4 is 2. 2 times 0.41. And again, we get 0.82 meters. All right, so that's kind of a thorough run through of how we approach angle launch problem. Different problems we'll ask are different things, but the idea that we're trying to figure out total flight time and peak time is pretty important here. Okay. All right. Any questions on that? It's a lot. Stop my recording here.